I realised on Sunday that we probably could have had cross product this week because we only have 27 slides this week, but you never know, it might take us 3 hours to get through this. We're going to be doing equations of lines and planes in 3D. So in 2D, we have the equation of the line can be found from the point xy, so a point on the line, and the slope of the line. So if we had, say, here's a line, we'd find the gradient, and if we had a point, we can just substitute it into this equation here. We'd have y minus y naught is equal to the gradient times by x minus x naught, and we'll be left with something in the format of y is equal to mx plus some constant. In 3D space, however, we can also determine the equation of the line with a point, but also the direction. The thing about 3D, the direction is defined by the vector. So if we know the vector that is parallel to the line and a point, we can actually describe a line in three-dimensional space. But let's look at it in the 2D case, and then we'll extrapolate to 3D. In the 2D case, this is where I'm going to use different colours. If we have a point, so we want to find the vector equation of the line that passes through the point 1, 5 and is parallel to the vector v is equal to 3i minus 2j. So if I draw, well, let me put this in here. 0, 1, 2, 3, 4, 5, 7, 13, 14. So I just put my axis numbers, scale, units. There we go. So if I put in my point, the point is 1, 5. That's our point. So if I draw my vector in, I know you're probably going to go, why am I using colours of purple and stuff, but I do like bright colours. Okay, so if I draw my vector in from this point, so the vector is 3, so I'm drawing it from the line 3 minus 2. So here's our vector. From that point, do you realise that if I draw another one, and I could do the minus vector, so the minus vector, what's that doing? What's that tracing? If I keep drawing vectors, just adding them. Yeah, they're actually following the line. In fact, if I turn around and say, well, if I do the position vector from the origin to P, so that's my position vector, then any point, say any point here, so that's a point x, so that's the position point vector x. Any point, so our position vector x is in fact OP, so OP plus some multiple of vector v. So what this is doing, this vector OP is actually, the tip of that vector is tracing the line. So that's a scalar multiple. It could be a half. If it's 2, so we would have 1, 5 plus 2, 3 minus 2. That would give us 1 plus 6, so 7. 5 plus minus 4, so it's actually 2. No, 5 plus minus 4 is 1. And if you look at it, that point there is in fact 7, 1. So that's when I'm multiplying by 2. And if I multiply it by a negative number, it actually goes in the opposite direction. So this thing is actually tracing OX tip traces the line. Okay? So, and the resulting X and Y gives you the points on the line. So our X in this case is defined by 1 plus 3t, and our Y is defined by 5 minus 2t. Isn't that nifty? And the thing is, in 3D, the same thing happens. You can see this easily. You can see this easily in 2 dimensions. It's not so easy to see it in three dimensions because, you know, there's the extra dimension. But the same principle applies, that you'll have the vector tracing the direction, so you take multiple, and you will basically have the position vector to the point plus scalar multiple multiply the vector that's parallel to the line. All good? Any questions? Yeah? This one here? So if we look here, we have the position vector here. Our position vector is 1, 5. Okay? There's our V, and the thing is, it's actually tracing it. So your position vector tells you the point on the line, and we're adding the next vector. So if I had drawn our OX here, then we have OP plus 2V is equal to, so this is head, tail, and then tail, tail, head, head. So this is actually equal to OX. And this thing is just going to be tracing up and down the line. Okay? The T will depend on what the point is. So if you have 1/4 this length, you're looking at a point here. Okay? So 1 unit, then you're actually looking at the point 4, 3, which makes sense because you'll actually have 1 plus 3, which is 4, 5 minus 2, which is 3. Okay? So, moving on. Yeah? Is T always given? T is a arbitrary constant in the sense, not arbitrary constant, it's a pronumeral which you actually put your values in. Okay? So it actually gives you all the points along the line. Okay? If you were told to find 1/4 of the length of the vector, then you'd put in, so you'd actually, you mean a point that's sort of like 1/4 of the way down? Usually with regards to t, you're actually looking to see whether you'll have a point at this point. Where does it intersect, say, a plane? Okay, so these things here, they're parametric equation of a line. So with regards to t, and you can actually use them to substitute it into equations of planes to find out particular points. Okay, so moving on. If we let OP, once again the conversion, be the position vector of a given point on the line, here, so for the previous example, our OP was in fact 1, 5, so the vector 1, 5, or we could say it's I plus 5j. And if we recall, the vector that we were given tells us the direction. So this vector tells us the direction of the line. Then we add scalar multiples of v onto our position vector, OP, to get all the other points on the line. So we are basically left with OX, so this is our point along the line, is equal to OP plus TV. And this thing here is called the vector equation of the line through the point P. So your P is your origin, starting point almost. Now the other equation that we had, so we had OX is equal to 1, 5, T, 3 minus 2. So our x coordinate is going to be 1 plus 3t, which is here, and our y component is 5 minus 2t, and these things here are called the parametric equation of the line. And we can extrapolate this into 3D by just having a z coordinate. Okay, so can I flip the page? Yeah? No? Some people still going? It's all right. There's time. Okay. If we have a point, a line that passes through x, y, x0, y0, z0, and whose direction is given by the vector ABC, then our x component is x0 plus at, so this is a, and that's t is just your pro numeral, y0 plus at, and z0 plus at. Okay, you can eliminate the t, and then what we get is what is known as the symmetric equation of the line. So we eliminate by doing x minus x0 divided by a is equal to t. So y minus y0 divided by b is equal to t. And z minus z0 divided by c is equal to t. And of course this is all t, so they're all equal to each other. And this is our symmetric equation of the line. Yep. Because I am very, very silly. Extremely silly. And of course, this is now saved in place. That's a B, and that's a C. Thank you for picking that up. I can only say it's really early in the morning. Let me just write those in. Yeah, all good? All right, so let's save this.